In this video, we will discuss another important probability rule known as the addition rule. But before we do that, the standard deck of playing cards are often used to describe probability concepts. So let's go through, discuss the key features of the standard deck of playing cards before we move forward. Notice that there are 4 different families of cards. The ones across the top here, those are called the clubs. These ones are called the spades. The clubs and the spades are black cards. These ones are called the hearts, and these ones are called the diamonds. And the hearts and diamonds are red cards. Then each family has the same type of member. The A is called the aces. The 2s are the 2s, the 3s are the 3s, so on and so forth, all the way up to the 10s are the 10s. So each family has a 10, for example. Then each of them has a J. The J's are called the jacks. Each family has a Q, which is called, they're called the queens, and each has a K, which are called the kings. And there's a total of 52 cards. Each family has 13 cards. 13 times 4 would give you 52. Let's now begin to look at the addition rule. We are going to spend time trying to discover the addition rule. And to do that, we're going to look at an example. So if one card is drawn at random, that's our probability experiment. What's the probability of getting a king? Notice there are 4 kings out of the total, again, is 52. So there's a 4 in 52 chance that when you draw one card at random, that you would get a king. If you were to do this again with the entire deck, what would be the likelihood that you would pull a 6 when drawing one card? Well, there are 4 desired outcomes. There's 4 6s out of the total 52 outcomes. So there's a 4 in 52 chance that you would get a 6 when drawing one card at random. You will see when we state the addition rule in a bit that the addition rule involves looking at the probability of an event A occurring or an event B occurring. Probability of A and then B occurring is a multiplication rule problem. Probability of A or B occurring is an addition rule problem. So let's now figure out, if you were to draw one card from the entire deck at random, what's the probability of getting a king or a 6? Well, in that case, there's 1, 2, 3, 4, 5, 6, 7, 8 total desired outcomes out of the total of 52 outcomes. So there'd be an 8 in 52 chance of us getting a king or a 6. So, do you see a conjecture that we could possibly make? Conjecture means like a hypothesis that we could make that tells us how to get the probability of king or 6 from these two. Well, if you notice, we literally just add these two up and we get that one. So it appears that when you have the probability of A or B occurring, you just have to add the probabilities of each of them. Right? The probability of getting a king or a 6 is the probability of getting a king plus the probability of getting a 6. That's our current conjecture or hypothesis. Let's try this with another example to test this conjecture. If one card is drawn at random, what's the probability of getting a king? Well, we actually just did that, but let's go through it again. There's a 4 in 52 chance of getting a king. Then if you drew one card from the entire deck and drew it at random, what's the probability now of getting a diamond? Well, in that case, there are 13 desired cards out of 52. So there's a 13 in 52 chance that you would get a diamond. Now, just like on the previous screen, what's the probability of getting a king or a diamond? If you draw one card from the deck at random, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 desired outcomes out of 52. So there's a 16 in 52 chance that you will get a king or a diamond when you draw one card at random from the deck. Did our conjecture hold up? Our conjecture was that you could take this thing, add this, and that would give you this. Well, if you look, 450 seconds plus 1350 seconds is 1750 seconds, not 1650 seconds. So what that means is our conjecture previously was wrong. Why didn't it work out? How come the probability of king or diamond how come it's not the probability of the king plus probability of getting a diamond? That was our previous conjecture, but it's not working. So this is not true. Well, here's the problem. If you notice, this 13 right here contains all 13 of these cards, one of which is the king of diamond. This 4 right here includes all 4 of these kings, one of which is the king of diamond. So essentially, the king of diamond is being counted in both that 4 and in that 13. So it's being counted twice. That means we need to take that off. So 4 50-seconds plus 13 50-seconds is 17 50-seconds, but we need to subtract off that one repetition of the king of diamond. If we do that, we then get the probability of getting a king or a diamond is equal to the probability of getting a king plus the probability of getting a diamond minus the probability of getting something that's simultaneously both a king and a diamond. I'll just put that word down here. This now works. Probability of getting a king is 4 50-seconds. Probability of getting a diamond is 13 50-seconds. And then the probability of getting a card that's simultaneously both a king and a diamond is 1 out of 52. That's that overlap that we don't want. This is the 1 out of 52 is where the counted the king of diamonds twice. And now, if we do that addition and subtraction, we get 16 out of 52, which is precisely what we got when we counted it. This right here is true in general. And the generalized version of this is what we call the addition formula. Let's take a look at it. The addition rule states that the probability that events A or B will occur, the or is absolutely essential here, not and, that A or B will occur is the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B occurring simultaneously. Again, this is taking care of the overlap. It's subtracting off potential overlap in the events. We will discuss what we mean by overlap in the events shortly. Let's first take a look at an example. As you can see here, I have a contingency table example that we actually looked at in a previous screencast. As a reminder, a store manager thinks that playing music in the store will increase her overall sales. She conducted an experiment for a period of time and found the following results. Each of these numbers, again, we took to mean in hours. So now I want to know, what's the probability that there were high sales or music was not playing? Keyword is or here. If that was and, it would be a totally different question. So what's the probability that there were high sales or music was not playing? Well, let's first use some notation here. I'm going to use H to represent high sales. I'm going to represent, or let N represent music was not playing. So we want the probability of H or N. Well, according to the addition rule, you would add the individual probabilities, probability of H plus the probability of N, and then you need to subtract off the probability of H and N occurring simultaneously. So we can now compute each of these probabilities. The probability that there were high sales. There were 46 total hours where there were high sales out of 88 total hours of the experiment. So this is 46 out of 88. Plus, what's the probability that there was no music? Well, there were 32 hours for which there were no music out of the total of 88 hours for which they did the study. So this is 32 out of 88. And then minus, what's the probability that they simultaneously had high sales and music was not playing? Well, high sales and music was not playing is right here. 14 hours there were high sales with no music playing. So this is just 14 out of the total of 88. That is the overlap part that we had to subtract out. That 14 is technically part of that number and that number, so that's why we subtract it off once so that it doesn't repeat. And of course, if we just do the arithmetic here, we have 78 minus 14 is 64. Hence, there was a 64 and 88 chance that there were high sales or music was not playing. Now on this final screen, we want to revisit the first screen to talk about what it means for events to overlap. So technically, we saw that the probability of getting a king is 4 in 52. The probability of getting a 6 is 4 in 52. Then the probability of getting a king or a 6 was 8 in 52. And we noticed that this plus this is equal to that. But that conjecture did not work in general. So let's see if the actual addition rule does apply here still. According to the addition rule, we have the probability of k or 6 is equal to the probability of k plus the probability of 6 minus the probability of getting k and 6 simultaneously. So again, the probability of getting a king is 4 out of 52. The probability of getting a 6 is 4 out of 52. Minus when you're drawing one card, the probability of simultaneously getting a king and a 6 is 0 out of 52 because there is no card that's both a king and a 6. So technically, 4 50-seconds plus 4 50-seconds minus 0 50-seconds is 8 50-seconds. So the addition rule still works, even when there is no overlap between the two events. When we had diamonds overlapping with kings, then we had to subtract stuff off. Here we don't need to subtract anything off, but it ends up being 0 in the formula. That's why it doesn't matter. So the addition rule applies in general. We have a special name for two events that do not overlap. They are called mutually exclusive events. Kings and 6s are mutually exclusive. They're two events that cannot overlap. Whereas kings and diamonds, they were not mutually exclusive. So the addition formula works all the time. However, the minus part ends up being 0 if you're dealing with mutually exclusive events.